The title of the next paper is Modeling and the Implementation of an Adaptive Vehicle Light Management System. This paper has 4 authors. The authors are from Croatia and Serbia. And the presenter is Ante. Okay, Ante, please.
My name is Ante, and today I'm going to be talking about this modeling and implementation of an adaptive vehicle light management system. These kind of systems, often called the adaptive front lighting systems or the AFS, are improvement to usually classical static lights, which are still used in most vehicles today. These systems have dynamic behavior. They use different sensors and actuators to adapt to the changing vehicle surroundings, traffic conditions, and so on. This way, the road safety and driving comfort is greatly improved. However, these systems are still usually implemented only in high-end vehicles, and they are sparsely used. And also in other work we've seen, usually just one feature is covered. So we saw some room for improvement here, and we decided to make a more complete system and which will cover multiple AFS functionalities. And besides that, we wanted to develop a certain framework for these systems, software development, to show how they could be more easily made. Then a logical thing to do was to try and develop our own idea of an AFS system using this framework. For this system of ours, we've selected multiple features most commonly used in similar systems, which are horizontal and vertical beam adjustment, adjustable headlight beam, and cornering light. All of them use some kind of a sensor to utilize data from the environment, for example, speed sensor, vehicle pitch sensor, or a gyroscope, and so on. The actuator, for the most part, is a special headlamp with stepper motors capable of moving in all directions in certain range, of course. And there are some more advanced solutions which use LED matrix lights or laser beams, but we deemed this was enough for our showcase. Additionally, we added CAN communication protocol in our system, and it's important to say that it was designed following the AUTOSAR architecture rules, which enable us to build a modular and scalable model of software. So the first step in developing a software system software like this is designing software components or SVCs, which are basically represent individual system parts, each doing its own task, and they exchange information between them, and together they build a complete system software. They fall in one of 3 categories: a sensor, actuator, or a center control SVCs. For each of them, after we design them, the appropriate data types had to be created to store the data, and the port interfaces had to be created to communicate, so that SVCs could communicate and transfer the data. Sensor components are used to read data from sensors. Central component uses that data to calculate the proper response, and actuator SVCs write data to the actuators, who then does something. For components to do something, the runnable entities were created. They are called the runnables. And they have some trigger rules which were also assigned, so they know when and how often they do something. And after we done these components, they are connected, and you get something like this, or exactly this. This is a resulting software model, where on the left side there are software SVCs, sensor SVCs. On the right side, there are actuator SVCs, And in the middle is the central SVC, which is in charge of data processing, and basically it's the brain of the system. There can also be seen all the port connections, and on the bottom there is a special SVC which is used to simulate outside data later on. The system software, the system software had to be further configured. This was only a model until now. Now the configuration includes setting some behavioral rules, the runtime environment, and the middleware layer. Also, some OS tasks were made as they are needed for runnables to be executed in, and the tasks were scheduled, so the execution order was set. After that, an important part was done, and that's the algorithm implementation. Algorithms were implemented as C code functions inside the runnables, which were empty until now. So the sensor and actuator components got some simple read and write functions, while more complex code was written for each of the functionalities, like horizontal or vertical movement and so on, and it was put in central SVC runnable. These functions calculate dynamic behavior of a system based on sensor inputs. In the end, also, we've done a simulation. We had to create a simulation environment which enabled us to easily interact and visually observe the system behavior. It was done using a Kanui software, which enabled us to build this graphical simulation panel and link it to our software model. And also, we've done some QA measures, mainly the unit testing, to prove that our functions were acting as expected, and we implemented some error handling, so the error codes are sent if some problems arise. In the next slide, we can see, in this slide, we can see this interactive simulation panel, which was used to test the system behavior. It is not interactive now, but believe me, it worked. The left side shows the part where you can simulate what kind of input data from the environment you want. For example, vehicle speed, other vehicle parameters, vehicle turn angle, and so on. And on the right side, in these gauges and lights, you can see how it acts. So as you move something on the left side, it provided output on the right side and showed how the vehicle lights would behave in real time. And to conclude, we designed our AFS system using multiple features, and it was implemented using this framework, which comprises of a few key phases, which are modeling, configuration, code implementation, testing, and simulation. And we used modern techniques and tools to do that, which enabled us to do it with relative ease. The resulting system behaved as expected, which was shown in simulation and both in unit testing. And we can say our objectives were met. This also shows how AFS systems or other similar systems can be built, and will probably find their way into more widespread use. And yes, that was all. Thank you for your attention.
Okay, thank you. Thank you very much, the speakers' excellent presentation. So, any question from authors, or I'm sorry, if any question from audience, any question or comment from audience? Okay, I have a simple question. So in your study, what is the most difficult part when you develop the proposed the light management system? Thank you.
The most difficult part was
the most difficult part.
Yes, the most difficult part was probably the configuration of a system, because there are many different variables you need to adjust. You need to put the communication rules and so on. So yes, that was the most challenging thing to do.
Okay. Thank you very much for your answer. So
thank you.
Thank you. So any question or comment? Any other question or comment from the audience? Okay. If no any other question, I would like to thank the excellent presentation again. Thank you. Thank you very much.